124 light-years from Earth, the James Webb Space Telescope detected something in an alien atmosphere that scientists didn't expect to see. On our planet, dimethyl sulfide is produced almost exclusively by microscopic ocean life, phytoplankton releasing this gas as they convert sunlight into energy. Finding even a trace of it elsewhere would represent the most promising atmospheric biosignature ever detected beyond our solar system. But K2-18b is not Earth. It's 8.6 times more massive, orbits a dim red star in the constellation Leo, and belongs to a class of planets, sub-Neptunes, that simply doesn't exist in our solar system. And when independent research teams reanalyzed the same data, they found something scientists deal with constantly in cutting-edge astronomy: competing interpretations of what the telescope actually recorded. In this video, we'll explore what Webb observed in K2-18b's atmosphere, how different teams interpreted the same spectral data, and what this reveals about the challenges of detecting potential signs of life across interstellar distances. K2-18b represents one of astronomy's most perplexing categories: sub-Neptunes. These worlds, with sizes between Earth and Neptune, are the most common type of planet in our galaxy. Yet nothing like them exists in our solar system, leaving scientists without a local comparison to understand their true nature. When NASA's Kepler Space Telescope discovered K2-18b in 2015 during its K2 mission, astronomers immediately noted its position in the habitable zone, the region around a star where temperatures could allow liquid water to exist. At 2.6 times Earth's radius and orbiting a cool M-dwarf star every 33 days, K2-18b became a target for atmospheric investigation. Early observations with the Hubble Space Telescope between 2016 and 2017 suggested the presence of water vapor in the planet's atmosphere. Multiple research teams published analyses indicating this habitable zone world might harbor H2O in its skies, a finding that generated significant interest in the exoplanet community. But subsequent atmospheric models revealed a problem. Self-consistent climate simulations proposed that the spectral features Hubble detected might actually be methane, not water vapor. The debate highlighted a fundamental challenge. Without directly sampling these distant atmospheres, scientists must interpret subtle variations in starlight, and those interpretations can differ dramatically depending on the models used. The James Webb Space Telescope targeted K2-18b as part of JWST General Observer Program 2722, led by Niku Madhusudan at the University of Cambridge's Institute of Astronomy. The observations represented a significant investment of telescope time on one of the most oversubscribed scientific instruments ever launched. On June 1, 2023, Webb's NIRISS instrument, the Near-Infrared Imager and Slitless Spectrograph, contributed by the Canadian Space Agency, captured K2-18b transiting its star using the single-object slitless spectroscopy mode. The observation lasted 4.9 hours, covering one complete transit as the planet passed in front of K2-18 from Webb's perspective. 7 months earlier, on January 20, 2023, Webb's NIRSpec instrument, the near-infrared spectrograph provided by the European Space Agency, observed another transit. This observation used the Bright Object Time Series mode with the G395H grating, dispersing the starlight across two detectors and capturing wavelengths from 2.73 to 5.2 micrometers. Together, these two instruments provided spectral coverage from 0.8 to 5.3 micrometers, the near-infrared range where many atmospheric molecules leave distinctive absorption signatures. Each transit observation captured starlight filtering through K2-18b's atmosphere, with specific molecules absorbing particular wavelengths and creating a chemical fingerprint in the transmitted spectrum. Transit spectroscopy works by measuring the difference between two observations: the star's baseline brightness when the planet is not blocking it, and the slight dimming when the planet crosses in front. But the technique doesn't just measure the dimming, it analyzes which wavelengths of starlight dim slightly more than others. When K2-18b passes in front of its star, a tiny fraction of starlight, less than 1%, filters through the planet's upper atmosphere before reaching Webb's detectors. Atmospheric molecules absorb specific wavelengths based on their chemical structure. Methane molecules, for instance, absorb strongly around 3.3 micrometers. Carbon dioxide absorbs near 4.3 micrometers. Water vapor creates absorption features across multiple wavelength bands. The challenge lies in the signal strength. The additional dimming caused by atmospheric absorption represents a change of only a few hundred parts per million, hundredths of a percent of the star's total brightness. At 124 light-years distance, detecting these minute variations requires extraordinarily sensitive instruments and careful data processing to separate real atmospheric signals from instrumental noise and stellar variability. Webb's instruments record these observations as spectroscopic light curves, measurements of brightness at hundreds of different wavelengths throughout the transit. Research teams then process this raw data through reduction pipelines, removing systematic errors, correcting for detector artifacts, and extracting the planetary transmission spectrum. But different pipelines make different choices about noise correction, outlier rejection, and baseline fitting, and these choices can affect the final spectrum. The initial James Webb Space Telescope observations published by Madhusudan's team in 2023 revealed several prominent absorption features in K2-18b's transmission spectrum. The most significant detection was methane, showing clear absorption bands around 3.3 micrometers, with approximately 4 sigma statistical confidence, meaning less than a 0.006% probability the signal occurred by random chance. Carbon dioxide appeared to show absorption near 4.3 micrometers, though this detection proved less robust in subsequent analyses. The spectrum also indicated an absence of ammonia, a molecule that would typically be expected in a hydrogen-rich atmosphere at K2-18b's temperature. The lack of ammonia represented an important constraint, something the atmosphere appeared not to contain. But the most controversial signal appeared around 3.4 micrometers. The spectrum showed a feature that the Cambridge team tentatively attributed to dimethyl sulfide, or DMS. The statistical significance reached approximately 3 sigma, meaning roughly a 0.3% probability of occurring by chance. In scientific terminology, this falls below the 5 sigma threshold required for claiming a definitive detection. Water vapor, surprisingly, showed very weak or absent signatures in the JWST data, contradicting the earlier Hubble observations that had suggested substantial H2O content. The JWST observations indicated water concentrations below 0.1% of the atmosphere, far lower than previous estimates. This suggested either that the atmosphere has an efficient cold trap preventing water from reaching observable altitudes, or that Hubble's water signal was indeed methane misidentified. The Cambridge team proposed that K2-18b might represent a Hycean world, a portmanteau of hydrogen and ocean. This model suggested a planet with a liquid water ocean beneath a hydrogen-rich atmosphere. The high methane to ammonia ratio and the presence of carbon dioxide aligned with predictions for such a configuration, where an underlying ocean would dissolve ammonia while allowing methane and CO2 to remain in the atmosphere. The tentative DMS signal strengthened this interpretation in their view. On Earth, dimethyl sulfide is produced almost exclusively by marine phytoplankton, microscopic organisms that release DMS as a byproduct of their metabolism. If the signal represented genuine DMS at the concentrations indicated, thousands of times higher than Earth's atmospheric levels, it could suggest biological activity producing the molecule at extraordinary rates. However, alternative interpretations emerged as other research teams examined the same data. A comprehensive reanalysis led by Luis Wellbanks at Arizona State University and Stephen Schmidt's team applied multiple independent data reduction pipelines and over 250 different atmospheric retrieval models to the JWST observations. Their analysis confirmed the methane detection, but found no statistically reliable evidence for either carbon dioxide or dimethyl sulfide. The Wellbank study proposed that K2-18b could be explained as an oxygen-poor mini-Neptune, a gas-rich world with a deep hydrogen atmosphere and no liquid water surface. Other hydrocarbons in the atmosphere, they noted, could produce spectral features similar to DMS, making the original attribution ambiguous. The absence of ethane in the spectrum, which biological processes producing large amounts of DMS would likely generate, raised further questions about the biosignature interpretation. Laboratory experiments in 2024 demonstrated that DMS can form through abiotic photochemical processes under conditions simulating hydrogen-rich exoplanet atmospheres, providing a non-biological explanation for the molecule's potential presence. The debate illustrated a fundamental challenge. The same spectral data, processed through different analytical frameworks, can yield substantially different atmospheric compositions. The K2-18b observations do not confirm the presence of dimethyl sulfide. The 3 sigma statistical significance of the original detection means there remains a 0.3% probability the signal occurred purely by chance, far above the 5 sigma threshold astronomers require for definitive discoveries. Multiple independent reanalyses found no reliable evidence for DMS when applying different data processing methods. Even if dimethyl sulfide exists in K2-18b's atmosphere, its presence would not confirm biological activity. The 2024 laboratory demonstrations of abiotic DMS formation showed that photochemical reactions in hydrogen-rich atmospheres can produce the molecule without any living organisms. DMS has also been detected in cometary and interstellar environments, regions where life almost certainly does not exist. The observations cannot determine whether K2-18b possesses a liquid water ocean. Transit spectroscopy samples only the upper atmosphere, the region through which starlight passes during the planet's silhouette crossing. The technique provides no direct information about what lies beneath, whether a liquid ocean, a supercritical water layer, or simply more atmosphere extending to a rocky or icy interior. The planet's size and mass present additional constraints. At 8.6 times Earth's mass and 2.6 times Earth's radius, K2-18b likely possesses a massive, high-pressure ice mantle similar to Neptune's interior, overlaid by a hydrogen envelope. The surface pressure, if a surface even exists, would reach levels where traditional notions of habitability break down. The hydrogen atmosphere itself makes up at most 6.2% of the planet's total mass. Temperature calculations indicate K2-18b receives stellar radiation similar to what Earth receives from the Sun. However, the planet's thick atmosphere creates unknown temperature gradients between its upper observable layers and any potential deeper regions. Without understanding these thermal structures, scientists cannot determine whether conditions anywhere in the atmosphere or below could support biochemistry as we understand it. While these conditions could theoretically support certain forms of life, this discovery does not confirm the presence of biological organism. The K2-18b controversy follows a familiar pattern in astrobiology. In 2020, researchers announced the detection of phosphine in Venus's atmosphere, a molecule that, like DMS, is primarily produced by life on Earth. The initial detection reached approximately 6 sigma significance, seemingly above the threshold for reliable discovery. Yet subsequent reanalyses questioned whether the spectral feature represented phosphine at all, proposing that sulfur dioxide or instrument artifacts could explain the signal. Similarly, in 1996, scientists examining the Allen Hills 84001 meteorite from Mars announced evidence of fossilized bacteria, including magnetite crystals that appeared biological in origin. Further research revealed that non-biological processes could form identical magnetite structures, and the initial analysis may have been based on a selective interpretation of the data. The claim of ancient Martian life remains unconfirmed. These cases illustrate a consistent challenge. Molecules or features that serve as biosignatures on Earth do not necessarily indicate life elsewhere. Context matters enormously. Earth's atmosphere contains oxygen because photosynthetic organisms have been producing it for billions of years. But oxygen can also form through photochemical water splitting on planets without life. The biosignature interpretation requires not just detecting a molecule, but ruling out all plausible abiotic formation pathways. K2-18b represents the first sub-Neptune where JWST has detected carbon-bearing molecules in the habitable zone. Other sub-Neptunes observed by Webb have shown thick cloud layers that obscure their atmospheric chemistry, making K2-18b's relatively clear atmosphere scientifically valuable regardless of its composition. The planet's characterization provides crucial data for understanding this extremely common but poorly understood class of worlds. The ongoing debate has prompted proposals for additional JWST observations. The Cambridge team estimates that 16 to 24 additional hours of observation time could potentially push the DMS signal, if real, above the 5 sigma threshold. However, telescope time on JWST remains extraordinarily competitive, with hundreds of proposed observations competing for limited scheduling. NASA's Goddard Space Flight Center has maintained involvement in the K2-18b analysis through its exoplanet science teams. A NASA-led reanalysis uploaded to the archive preprint server in July 2025 incorporated multiple independent analytical approaches through Bayesian model comparison, allowing 3 separate teams to develop interpretations based on different atmospheric composition scenarios. The study confirmed K2-18b's water-rich nature while finding no conclusive evidence crossing the 5 sigma threshold for DMS. The European Space Agency, which contributed the NIRSpec instrument to JWST, has continued supporting atmospheric characterization programs for sub-Neptune's in habitable zones. ESA's emphasis remains on developing robust retrieval methods that account for systematic uncertainties in spectroscopic observations. The agency's scientists have noted that K2-18b demonstrates both the capabilities and limitations of current transmission spectroscopy techniques. The K2-18b observations have influenced how research teams approach biosignature claims. Multiple institutions now emphasize the importance of independent data reduction pipelines and comprehensive model testing before publication. The Space Telescope Science Institute in Baltimore has facilitated data sharing protocols, allowing external teams to validate initial findings using alternative analytical frameworks. Atmospheric retrieval codes are being refined in response to the K2-18b debate. Research groups have developed methods to quantify how different choices in noise correction, baseline fitting, and opacity modeling affect final composition estimates. These improvements aim to distinguish robust detections from analysis-dependent results, strengthening the field's ability to characterize exoplanet atmospheres reliably. The controversy has also prompted discussions about observation strategies for future biosignature searches. Scientists are proposing multi-instrument approaches that observe the same target across different wavelength ranges, providing cross-validation of molecular detections. Additional observations with JWST's MIRI instrument in the mid-infrared range could help confirm or refute the presence of molecules detected in near-infrared observations. K2-18b represents a crucial test case for how scientists will search for life beyond Earth over the coming decades. The debate surrounding its atmospheric composition illustrates that detecting biosignatures requires not just finding molecules, but systematically ruling out non-biological explanations, a far more challenging task than initial detections suggest. Sub-Neptunes constitute the most common planetary type in our galaxy, yet they remain poorly understood because nothing comparable exists in our solar system. K2-18b provides one of the first detailed atmospheric characterizations of a sub-Neptune in the habitable zone, offering insights into how these ubiquitous worlds form and evolve. Understanding their atmospheric chemistry constrains models of planetary formation throughout the galaxy. The methodological lessons from K2-18b extend beyond this single planet. The discovery that different data reduction pipelines and retrieval frameworks can produce substantially different atmospheric compositions from identical observations reveals systematic challenges in exoplanet spectroscopy. Addressing these challenges strengthens the field's ability to make reliable claims about distant worlds. The case demonstrates the essential role of scientific skepticism and independent verification. The original tentative detection prompted multiple research teams to reanalyze the data using alternative methods, exactly how science should function when extraordinary claims emerge. This process, though sometimes appearing as disagreement, represents the scientific method working as designed to separate robust findings from analysis artifacts. Future missions will build on JWST's capabilities. NASA's Habitable Worlds Observatory, currently in early planning stages, aims to directly image Earth-like planets around Sun-like stars and analyze their atmospheres for biosignatures. The lessons learned from interpreting K2-18b's spectrum inform how these future observations will be designed, analyzed, and interpreted. Each controversial detection refines the standards for what constitutes convincing evidence of atmospheric chemistry, or, potentially, life itself.
The search continues,
K2-18b remains under investigation, with additional observations potentially scheduled as telescope time permits. Whether its atmosphere harbors dimethyl sulfide and what that molecule's presence might mean awaits further data. If you found this analysis valuable, consider subscribing to stay updated on developments in exoplanet atmospheric science. The comments section below offers a space to discuss the competing interpretations and what they reveal about the challenges of detecting life beyond Earth. The visuals in this video are educational illustrations based on scientific research, peer-reviewed studies, and official space agency publications. These visualizations are artistic interpretations intended to support public understanding.